Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Daniel Perley with us today. Hey, Dan.
Hello.
How you doing today?
Pretty good. A little bit tired.
Did you work out? Did you run around?
No, I actually just flew in from the US today. So a little bit jet lagged, but I'm here and happy to talk to you about my paper.
Well, thank you very much then for being willing to talk about your paper right after coming off an airplane or so. So what's your geolocation? Where are you at?
I'm in Liverpool.
Okay. Let's see. It is October 25th, 2021 as we do this recording. Has fall hit? Has winter hit in Liverpool?
It is actually a pleasant, sunny, and dry day. So it's a little bit cooler than summer would be, but it's doing its best to mimic the nice parts of year and not mimic the cold and damp parts of year, which is most of the year around here.
Oh, well, that's great. Well, great. You got some nicer weather here. We have definitely turned the corner. I'm in Phoenix, Arizona, and we have turned the corner, and it's definitely more into the fall. So we get we'll get down 50, 60 F in the morning, but still by the afternoon, we're up in the upper 80s or so mid 80s. So for a lot of people, that's still too hot, but yeah, we have turned the corner a bit. Cool. Dan, what do you like to do for research?
I work on transients generally, so anything that's powerful and luminous and explodes and can be detected with an astronomical facility, I'm interested in at some extent.
Very nice.
And so specifically, I've worked on things like gamma ray bursts and supernovae.
Okay. FRBs?
I have not done research in FRBs myself. I am interested in them, but that requires a whole other level of technical observational expertise that I haven't obtained yet. Maybe someday soon.
I like the word yet. There we go. Continually evolving. And that is going to bring us to this very lovely APJ article. The Zwicky Transit Facility Bright Transient Survey 2, a public statistical sample for exploring supernova demographics. And Dan, take us away.
Right. So the first thing you'll see is that this is paper 2, and it's probably going to be 2 of many. This is tied to 2 projects, one nested within the other. The larger project is the Zwicky Transient Facility, which many of the people who are reading this are probably already aware of, but for anyone who's viewing this and isn't aware of it yet, it's a very large optical time domain sky survey based out of Southern California, run by Caltech with partners worldwide, that essentially aims to map everything that's going on in the optical night sky on a time scale of approximately 2 to 3 days, and with some experiments aiming for shorter time scales as well. Okay. So it's a big telescope. It images half the sky every other night and sends us a constant stream of alerts to look at and find things in. And then within that, we have the Bright Transient Survey, which is what I'll be specifically talking about here, which is our effort to essentially catalog everything that meets a certain magnitude limit, and thereby do a magnitude limited survey of everything that's happening in the extragalactic transient sky. These are both very big projects, so you'll see lots of co-authors here, which help with this specific part of the paper, but this only sort of scratches the surface of the number of people who are involved in the ZTF project in general, from especially at Caltech on the engineering team, and also all around the world, who help build the thing, run the thing, and find all these interesting transients and follow them up and figure out what they are.
Cool. Very nice. Okay. There you go. Looks like, yeah, magnitude limited and GNR. Yeah. Okay.
Right. So so let me say a little bit more about the specifics of the project. So why do you do a magnitude limited survey? Well, obviously we've had optical time domain sky surveys for a while, and they have been finding lots of transients for a while, even before ZTF. If you look at the number of supernova discoveries, it's been pushing up into the hundreds and then thousands, and now it's reaching the 10,000s. And of course, that's great. We found all sorts of interesting new transient phenomena that we didn't know about before, sort of optical tidal disruptions events when stars are disrupted by black holes, or superluminous supernovae, or low luminosity transients, all sorts of things. But Simply knowing that they exist, while is interesting, isn't always going to answer all the questions that you want. You also would like to be systematic. You'd like to understand things like how many of them are there in the universe, how many bright ones versus fainter ones, high luminosity versus low luminosity, color distributions, what kinds of galaxies make what kinds of transients. And those are all sorts of things that are very hard to address unless you really have a good handle on the systematics. And the best way to have a handle on the systematics is to define some criteria around which you want to make sure you have captured and classified everything that meets those criteria. And the easiest criterion that one can come up with is a magnitude limit, because that is effectively unavoidable. You're always going to be unable to observe the faintest things. And so we have defined a magnitude limit here for this project, which is 19 magnitude in either of the filters that ZTF operates in, G band or R band. And we are aiming to identify everything in the survey that is potentially a supernova that is brighter than that magnitude, and classify everything that is brighter than specifically 18.5 magnitude. And with that, that can allow us to do the sorts of interesting systematic based calculations that we really are aiming at, like rates and galaxy preferences and things of that nature.
Cool. And you have some.
So sorry, go ahead.
You have some definition for what is a transient.
Right. So I use it. So the word transient means slightly different things to different people. And indeed, in the writing and the sharing of this paper around co-authors, it emerged that there are different people with different ideas about what a transient consists of. So the word, if you look it up in the dictionary, it has connotations of something that appears and goes away. So it's only there for a brief period of time before something happens, and either it goes somewhere else or simply ends.
Okay.
And so the definition that is used for this paper is an event with a pretty clear start time and an end time. That usually means it's coming from a catastrophic event that therefore can't recur. So this would exclude, obviously, variable stars, which usually have some periodicity. Sometimes it's irregular, but they will recur. So even though a recurring nova might recur only on timescales of 1,000 years, if we see it recur, we don't include it as a transient. If we think it might recur within a few years, because we know it's a class of phenomena that tends to recur in a few years, we don't call it a transient. But if it's something that we have only seen one of and we expect to only see one of, then we'll call it a transient for this purpose. 99% of operationally the things that we call transient are supernovae, though.
Okay.
With the remaining things being things like GRB afterglows, untitled disruption events, and novae.
Okay.
Extragalactic novae. We exclude anything that's within the galaxy as well.
Okay. Not that there's a lot of supernovae in the galaxy. So.
Yes, but there are novae, for example. So the problem is the novae tend to saturate the telescope or are behind too much dust to be able to say anything usefully systematic about. So it's not really the best facility for doing classical novae within the Milky Way galaxy. There are better experiments for that, but it's a decent facility to do novae within M31, for example. So we do include those, although it's not really the main focus of the paper. We're really focusing on sort of more distant galaxies that you really need to survey the whole sky to get meaningful statistics and systematics on.
Okay, cool. Let's maybe.
Right. So I see the next section that you've come up with is the section on the filter. So I can say a few things about that. So ZTF is trying to operate in an LSST-like way where it produces open alerts, and an alert appears anytime that it detects a change in a part of the sky. It takes a new image, it compares it to a reference image from early in the survey, differences them. And if the difference results in a positive or even a negative residual, that is potentially point spread function like, then that is registered as an alert. Alerts are then sent to the general public, although some private alerts in different surveys are not sent to the public, but this paper is only based on the public accessible alerts. Alerts contain information about how likely it is to be a real object, about its magnitude, about its location on the sky, about have there been any other alerts at this position and how many, et cetera, et cetera. The vast majority of the alerts that ZTF produces are not real supernovae. Many of them are artifacts, bad subtractions, variable stars, asteroids, things like that. We're not particularly interested in those. And so in the first part of this paper here, we discuss the procedure which we use to remove the alerts that are uninteresting and separate out only alerts that at least could potentially be a supernova on the basis of things like this deep learning based, we call it a real bogus score. It's a number between 0 and 1 that tells you how likely it is to be a real point spread function like transient and not a diffraction spike or something else.
Got it.
Of that nature.
Uh-huh.
But we also use, for example, whether it's on top of an existing star, if it's on top of a 12th magnitude catalog point source, we'll reject that. If it has been detected every day the survey has operated for the past 2 years, that means it's probably a variable star in error in AGN. We reject those as well. And only are displayed to us. So there's a sort of there's a computer vetting process that we filter the alerts. And the only ones that pass that and go to a second human vetting process are the ones that we think we can exclude obvious bad non-real events.
Okay.
And so that's what we describe here. But at the end of this process, there is a sort of a list of nightly events, sort of order 100 that are sent to scanners, which are people that are involved with the project. Some undergraduates are also helping us with this. Wow. And they're shown the images, they're shown a light curve, and they say, okay, is this possibly a supernova, or is it something that's definitely not a supernova? And you can sort of move it to the potential supernova pile, which then we will potentially use spectroscopic facilities to classify, or put it on a reject pile over which we don't see it again. Okay. Or we leave it and see what happens the next time the survey observes. So there's sort of 3 options.
Yeah. Okay.
In the manual vetting stage.
Very cool. Scanners. And at the end, you get something that looks like this.
Yes. So if you go to figure 1 there, which I see is poking up at the bottom, this shows the actual transients, things that have been spectroscopically confirmed after this process, after filtering, after scanning, after vetting, and then eventually after classification. So we use a couple of robotic telescopes and also classical facilities with regularly scheduled time to actually obtain the classifications. Of course, we also take classifications from the community. Plenty of other people out there are doing supernova science and getting classifications as well. We pull them all together, and we produce a catalog of what we think are all the classifications of all the bright events in the sky. And so the first figure here is largely meant to impress upon the reader that we are an all-sky survey. Over the course of the year, we do cover everything north of about minus 28 degrees. Mm-hmm. And we classify a lot of objects of various types. Mostly supernova type 1a, because supernova type 1a dominate every magnitude limited survey because they're both reasonably common and extremely luminous. Right. And so you get a lot of them when you have a magnitude cut as your primary criterion. Mm-hmm. But also plenty of other things as well.
Other, I like other.
Yes, so in this we've divided it by supernova 1a in orange, core collapse supernovae in green, and then some rarer things. TDEs are in red. You can see a few of them on there. Novae are gray. They're almost all in the same place, which is M31, because that's really the only, that M31 and M33 are the only galaxies that are near enough to detect a nova in with ZTF, since the Magellanic Clouds are in the southern hemisphere. And as I said, we don't really do the Milky Way. We actually exclude the Milky Way because there's too much confusion with stellar sources regardless, and too much extinction. And then a couple of interesting others that I'll describe later.
Oh, okay, cool.
Right, so if you keep scrolling down, that's kind of the end goal, is to produce these catalogs, but there's still a few other steps to get there. And there's also more than we want to do than just produce a catalog of here's what the classification is. A really nice thing about ZTF is that because it's all sky, it means that anytime a source is up at night, it means we're getting data on it. And because the survey is three-day cadence, at least over the period that went into this paper, we also get a pretty nicely sampled light curves. And because it's a 2-filter survey, we also get 2 filters. So this figure is really just to demonstrate the quality of the data that we are able to get. And so we have rise times for all these transients. We have color constraints at peak and at other phases. We have fade times. And so in addition to being able to have the simple classifications just by virtue of the standard survey operations, we also get really nice light curves. And so by putting these 2 things together, we can actually, first of all, make some more robust statements about our completeness than we would be able to be making if we only had a few data points here or there. And we can also actually address questions of light curve timescale, which I'll be discussing in a bit.
Very cool. Very nice. Very nice.
So you can go ahead and keep scrolling down.
Okay.
Now, to actually get to the thing that I showed before, where we had nicely separated the interesting transients as colors, and then, faint leaning gray in the background, what had been described as variables, we actually have to make some additional steps, because it's not always 100% obvious what's a variable. If something is in an AGN catalog, we know it's an AGN. If something's in a variable star catalog, we know it's a variable star. If we can see it doing some periodic behavior or stochastic behavior, one can usually flag it sort of by eye. But there's a little bit more than that you need to do, because sometimes we have very fast transients that are hard to separate from flares of faint stars in our own galaxy, cataclysmic variables and dwarf novae. And so we had one additional step, or really two additional steps, which are called the quality cut and the purity cut, or the quality filter and the purity filter.
Okay.
So the quality filter, which is I think the one above this, 2.3, is if you scroll back one page.
Yeah, I'm with you. We just have a little bandwidth lag. It's okay.
Yes. Okay. So so the quality filter is what we use to basically remove everything that doesn't actually have one of those nicely sampled light curves. So while we wish actually every light curve was like the ones I just showed you, in fact, that's not the case, because we do have weather, we do have sources that occur just as an object is getting too low to observe, because we also have seasons, the sun, the Earth moves around the sun, and therefore the positions of objects move relative to the sun. And so we can't observe some things for more than a week or two. And if that's the case, unless you're really good about getting a spectrum of something immediately, which is not always possible, you're not always able to tell what it is. And so rather than drive ourselves crazy trying to follow every single object, no matter how far south, east, west it is, if clouds move in for 2 weeks after it's discovered on all our spectrographs, we say we are going to actually restrict our classification efforts. I mean, we'll try to classify it anyway, but for the purposes of completeness and doing science, we're only going to consider events for which the survey was kind of operating at something close to the scheduled cadence, where at the time the object was at its peak light, where its light curve was at maximum, we have sort of enough observations on either side of that we can actually say some things about the light curve. And so the details of that are described here, about exactly how many observations we need at what phases relative to the time of maximum.
Right. Okay. So that's one filter.
Yep.
And then it looks like we have the purity filter.
So that ensures we can say things about the light curve. But of course, we also want to make sure it is a genuine extragalactic transient, because there are fast evolving things in our own galaxy that appear and go away too fast for us to classify. And there's a lot of them. So dwarf novae are largely the majority of these. These are basically white dwarfs that are having flares going on in their accretion disk from a faint companion. And can flare up by 5 or 7 or even more magnitudes erratically. And so we remove those by essentially removing anything that is evolving too fast and is not coming from a galaxy. So if we see something and it's in a galaxy, and galaxy is defined as basically as an extended object anywhere nearby, regardless of the light curve, we keep it. Okay. And if it has a time scale that is more than a few days long, we also keep it. If it doesn't meet either of those, if it's either coincident with the star or just there's nothing there and it's really fast, then we throw it away, because those are virtually every time that's happens that we were able to look at, it's a dwarf nova from a star in the Milky Way.
Cool. No, and just to be clear, so throw away as in throw away for this survey, but if somebody—
Throw away for the purpose of doing our statistics. So we do keep them. We have those in our catalog as well. And are served in our database just like everything else. So if people think that we're throwing away too many things, or they're actually interested in some of these potentially galactic sources, they can cross-check it there. Good. But for the purpose of doing our rate estimates and similar, we don't use those, because they're just too difficult to classify, and it would take us far too much effort to do so, even if we tried. We wouldn't be able to do the other kinds of science effectively.
Yep. So we got about.
Okay, so in section 3, we basically do an overview and say, how well did we actually perform? So we have the survey. It's been running for this period of time, about 2 years is what went into this paper. We have all these cuts. How well do we actually do? How many things did we succeed in classifying with the spectrograph, and how many kind of slipped away despite adding these cuts to make sure that it was nicely observable and so on. And we did pretty well. So we give some statistics here, which is that within the 2-year period of the survey, and for things that pass the quality cut, have a good light curve, and pass the purity cut so that they're not what appear to be obvious dwarf novae, we successfully classified 93% at that magnitude level.
Oh,
and
wow.
if you move the cut up, because you can always do this, you can subset it to higher and higher magnitude levels, or brighter and brighter magnitude levels. The completeness goes up, say it's 97% at 18th magnitude, and we classified everything brighter than 17th magnitude.
Excellent. Very nice.
And we classify a good fraction down all the way to 19th magnitude as well. So about 75% down to 19th magnitude.
Okay. Very good.
All right. So you can keep scrolling onward.
Rise times.
Yes. So this is just kind of illustrates how we came up with the cuts to establish the quality and purity filter. So this shows the rise time and fade time, and it shows the genuine supernovae, things that we successfully classified in color, and the things that are not genuine supernovae that we were able to determine by various features in the light curves, or actually through spectra of things that are definitely not supernovae. And you can see they pretty clearly separate in rise versus fade time space. So this motivated what we use for the purity cut there.
Okay.
Basically fast things, the bottom left corner, are almost universally not genuine supernovae. And even the few supernovae that are there, that's usually just because there was a data quality issue. There was a bad point in the light curve that caused it to look faster than it genuinely is in most cases. And also almost all those were in galaxies. And so even though their light curves were unusually short, we rescue them because they're in galaxies, as about 95% or more of supernovae end up being. And yes, over on the right, we see things that went unclassified, and just showing that the majority of them are things that are characteristic of supernovae. So these are the things that we missed. There's not many. As I said, it's about 7% of the sample.
Yeah. Yeah, certain magnitude. Yep. Mm-hmm. Very cool. And we got some of the totals here.
Yeah, so that gives our statistics. Nice big numbers, at least for the common thing. So more than 2,000 type 1a supernovae in this project, almost 1,000 core collapse supernovae, and pretty significant numbers, at least by standards of past surveys, of even pretty rare things. So 1BN supernovae, superluminous supernovae, tidal disruption events.
Yeah.
What we've lumped together as gap transients. These are low luminosity transients.
Right.
Decent numbers of all these things. And so even if you're interested in a fairly obscure thing, we actually have the makings of enough to start to do sample statistics.
These are going to be the cows and the
Yep.
Got it. The other cows. Very cool. Okay. We got some histograms and apparent magnitude distributions, if you want to cover.
Yeah, so this is a little bit more a visualization of our completeness statistics on the left. So we plot the cumulative total as a function of magnitude, and given that the universe is homogeneous and isotropic, that should be a 3/2 power law in Euclidean space, at least. And since we're only sensitive to things out to a redshift of 0.1, that's basically true for us. And if your actual observations follow that power law, that means you're doing a pretty good job of recovering everything regardless of magnitude. If you drop down below the power law, then you're not doing so well. And so this shows that down to 18.5, we're doing pretty well. We do start to fall a little bit below the completeness. So as you get to 18.5, we go a little bit below. And by the time you get to 19, which we don't even try to be 100% complete to 19, we just do our best at those levels. We are significantly below, but we still do pretty well.
Cool. Oh, yes.
And so the ratio of the theoretical versus the observed is up there, and that shows our differential completeness as a function of little magnitude bin.
Yep. Very cool.
And then over on the right, this is just demonstrating the kind of redshifts that we find things at, just to give an idea of the kind of survey that we're doing. So ZTF is not a large telescope. It's not even 2 meters. And so while its primary advantage is it has a big field of view, compared to other big field of view telescopes, it does go pretty deep, but we're still detecting supernova typically in the low redshift universe, although in the Hubble flow. So typically we find type 1a supernovae to redshifts of about 0.1 and core collapse supernova to redshifts of about 0.05, with a smattering of very luminous rarer transients at higher redshifts and the low luminosity transients, which you can only see very nearby at the lower redshifts, of course. For example, Novae are all practically at redshift 0.
Yes, nearby. Yep. Cool. I'm with you.
All right, and then just one more figure of showing kind of just what we're finding before we actually get into some of the things where we can use to take advantage of the high completeness that we have. If you go to figure 6. Which is a pie chart. So different people have different opinions on pie charts. Some people don't like pie charts, but there are lots of figures that look like this in all sort of big supernova survey papers. So
I find them
our own.
Yeah.
This basically just gives us a breakdown of what we find in this magnitude limited survey. So like other magnitude limited surveys, this excludes the non-transients, the variables. So other things that are actually successfully classified and are extragalactic transients, they're about 75% 1As, and 25% core collapse supernovae, and then a small number of other either lower luminosity or higher luminosity or rare transients. The core collapse supernovae are predominantly type 2, with a breakdown of subtypes there. We're not always able to distinguish different subtypes of different types of transients because that requires higher quality spectra than we're usually able to obtain. So the numbers here may not be truly reflective of the actual rates of things at the level of 2B versus 2P for people who are into supernova subtypes, but we're pretty robust for certainly type 1 versus type 2 and type 1A versus type 1B and 1C and so on.
Okay. Very good. I like those. Rapidly evolving stellar deaths.
All right. So that's what we found. But of course, other surveys have done things like this as well in the past. But what we really want to do is some real world science with them and actually say some useful things that are kind of unique. Because what I mentioned before, that's not completely unique, but the combination of such a big, powerful survey that's detecting so many transients and the quality of the light curves is really a new regime for any survey of this nature. And so what we can do here is we can take our light curves and measure some basic time scales. So as I mentioned before, we can measure sort of rise time, which we define as the time from half of the peak to the peak of the flux light curve. And we can measure the fade time, which is the time that it takes to go back to half of the peak. And we do that in whichever is the fastest filter, which is usually the G band, but occasionally ends up being the R band, depending on the nature of the object and the measurements. And so we can take those two times, we add them up. So that's basically the full width half max of the light curve. And we plot that on the x-axis, and then we take the absolute magnitude. So since we have the peak apparent magnitude, we just take the distance modulus and a basic K correction and plot the absolute magnitude. And we can put these two things on a scatter plot and just see how the different spectroscopic types, because we have the classifications of everything, and just see how things land in this parameter space. So much as early stellar astronomers took two very easy to determine measurements, the temperature and the luminosity, and made the famous HR diagram, we can take the time scale and the absolute magnitude and make an equivalent diagram, as previous surveys have done, but never at this scale. And so this kind of riotously colorful plot in the top left just shows everything on there all at once. And of course, this is very messy because it's not a nice sequence like the HR diagram is. It's a little more complicated than that. Transients are messy objects, but there nevertheless are trends. You can see there are colors that predominantly cluster together, separate from other colors. You can see the type 1As are a very tight cluster. And actually most of the scatter in that is instrumental or due to dust obscuration, because we don't correct for host galaxy dust obscuration, although we do correct for Milky Way dust obscuration. The type 2s are a different region of the diagram. The type 1Bs and 1Cs are a different region. The interacting transients are up on the top right. They're very luminous and long-lived, etc. So there's sort of different, and this is basically reflective of the different physics that is behind these different transients, type 1As and their connection between nickel and mass and total mass and energy. Type 2s are related to properties of the stellar envelope primarily. Interacting transients are reflecting the physics of the CSM and how that's distributed. and are also very efficient ways of producing electromagnetic radiation, so they tend to be luminous. And so basically that's what determined these. But really here, we're only trying to give people a taste of the observational parameter space that we will be exploring in the future as the survey continues.
Cool.
And just to demonstrate that even just these very, very basic things that can just be automated with scripts. I mean, obviously we did not calculate this painstakingly by hand for every object. I wrote a Python script to quickly calculate these things for every single thing and just apply them, and you can make these really nice looking plots and actually start to see correlations, which are also reflective of the physics. So the type 1a tilt there has to do with the famous Phillips acceleration, which is still not completely physically understood, but is known about. But there are also similar correlations underlying sort of all the different classes of transients that we have here.
Yeah.
With things that are longer being either more luminous or less luminous, that depends on the physics of the thing itself.
Right. Cool. Lovely plot.
So yes, this is a plot that we show prominently in our proposals and talks and everything. So it's really good to kind of demonstrate everything.
Very nice.
So in many ways, that's kind of, I think, the highlight of the paper is just the ability that we're able to do this. This is a very observationally driven paper. We're not trying to definitively answer every question. We're just trying to say these are the things that we can do really well with a survey like this. And to give you some idea, here's some basic plots that demonstrate that. But we can actually start to address some interesting questions that have been raised in the past.
Okay.
So the next few figures kind of go through a few of those. So one of them is the nature of the fastest transients, which is shown kind of in this figure. So this is everything that's really fast, kind of over on the left side of the diagram before. Fast things are a difficult parameter space to access. Fast and rare things, I mean, of course, if fast things were common and happening everywhere in our own galaxy and nearby galaxies, we'd characterize them well. And that's the case for example, fast classical novae, and it's true for stellar flares and things. But luminous fast phenomena that are luminous enough to be supernovae are both rare, and because they're fast, they're only observable for a short period of time, so they're hard to detect in the first place. Your survey has to have a short cadence, and then they're hard to classify because they're gone within a week. And if you don't get on it really fast and you're not really good with keeping up with your survey in absolute real time, you miss these things. And we're basically just as good in classifying class transients as we are at slower transients, at least down to sort of the 3 to 5 day time scale, below which you go below the survey cadence, and then we are going to start to miss things. But we're quite good at addressing the things in the 3 to 10 day time scale, which previous surveys have kind of struggled with. And so this basically shows the light curves of all the things that are fast enough and meet our quality cuts and the purity cut. And it's quite a smattering of different objects. There are a lot of different transients that can be fast depending on exactly what the circumstances are. The most famous of these by far is the one at top left, which happened right at the start of the survey. This is an absolutely phenomenal, exceptional transient, which dozens of papers have been written on, called the 80-2018 cow. I'd have to give a separate paper presentation to really get into the details of that. But this is a very rare, unusual transient, probably having to do with a central engine being produced in a failed collapse of a massive star, but there's other models for it as well. But there's other transients that can be fast. There's 2s and 2b's that have circumstellar material around them, and so there's a very fast shock breakout or shock cooling peak at the beginning of the light curve that can dominate the time scale. So even though some of these have second rises, those actually aren't really truly fast. But if the first peak is the brightest one, it registers as a fast transient for us. But what you can see is that's kind of the predominant source of thing. They're 2s and 2b's. And we think that's either some CSM around the transient or just a big inflated pre-explosion envelope, which is shocked by the supernova explosion, and that can produce a short-lived flash. That sometimes is followed by a radioactive supernova that's easily seen, and sometimes the supernova just kind of merges with the flash light curve, and you don't see much of it, as in that case.
Yeah.
There's also 1BNs, which is a known class of fast supernova that the origins are still not completely known for sure, but we detect those as well. So that's nice because we can start to make rate constraints.
Yes.
And 2Ns, which are again examples of transients with CSM that's being shocked. Normally 2Ns can actually be quite slow because they usually have extended CSM going out to very, very large radii. And so the shock keeps going on and producing light for a long time. But sometimes the CSM is not, at least the density drops off enough that you don't see that long-lived, and you just see the initial shock cooling in the beginning.
Right. Nice.
So, and this is kind of at least at the time was kind of a new thing, because before this point, largely the samples of things on this time scale were unclassified. So surveys like DES and Pan-STARRS put out sample papers of fast evolving transients, and they were largely sort of question mark, because either they weren't spectroscopically classified in time, or the spectra were only one was taken at peak light and it was at redshift 0.4 or something. So it wasn't a great spectrum because it was faint and it wasn't really clear what it was, but we can basically classify all of them.
Great.
And they're largely known categories of transients, with one exception.
All right. Those are the fast ones.
Yes. So we also have discussions of other parts of parameter space. So we go and look at low luminosity transients to see what the composition of those are. There's a smattering of things there. I'm not going to say too much here because we actually have separate sample papers that are more intensively devoted to that. To address the low luminosity transients, you actually don't necessarily want to do a magnitude limited survey. It's better to do a volume limited survey if you can, and target everything that's happening near known galaxies, because we know most galaxies that are nearby. And so it's not as essential to do a simple magnitude cut. And so there's different papers that are that have come out and will continue to come out that are addressing this population in particular, but we also have them in our survey, so we can still say some things. There are these calcium-rich transients, and also some interesting varieties of type 1b and type 1c supernovae that are just very weak and faint in this part of parameter space, as well as these things that are sometimes called intermediate luminosity red transients, which is really just an observational category, or luminous red novae, which are likewise an observational category, but probably most of them, these are things with like true gap luminosities right in between the novae around -9 and the supernovae around -16. Right. That might be coming from stellar mergers. So two low mass stars that are merging together to produce a single star.
Cool. You got some other categories. You got some of the superluminouses, the TDE.
Yes. Yep. So we don't say too much about superluminous transients because that's again going to be the subject of future papers that will say more about that population in detail. But we can, show that they connect pretty seamlessly with the less superluminous supernovae of the same classes. So the type 2 superluminous, kind of, if you go back to the big plot I showed before, largely just merge with the ordinary 2N. They form a continuum. The type 1c superluminous form a continuum with the 1c superluminous, although they might not all be the same population, but there's not sort of a gap in between them. Yeah, so if you look over the bottom right 2 panels there, you can see the superluminous. They're more long-lived than the ordinary 1Bs, but there are also long-lived low luminosity 1Bs. So I think there's some major open questions here as to whether these are actually 2 or 3 or more separate clusters. We tried to do sort of a k-means analysis here. It's not statistically significant yet, but there might be something interesting there or not, but there's not an obvious division simply in luminosity between these different categories yet.
Yeah. Okay. Cool. All right. Let's see. Rate measurements. That sounds kind of
yeah.
cool.
So I mean, the real reason to be extremely thorough about your systematics is to do rates. So rates are one of those things that sounds easy. You take everything within a volume, you count them up, you divide by the volume, you divide by your survey time scale, and you're done. But in practice are not so easy because certainly previous supernova surveys have they have cadence, so you miss fast things. They have survey holes because it's a season where things are up. Often it would observe a certain patch of the sky and then move to another patch of the sky and leave the first patch of the sky behind. So every light curve gets clipped at a certain point. There were completeness issues because you might be more likely to classify something because it's interesting or less interesting in some way or another. It's in a known galaxy or it's not in a known galaxy. It's slow, so it's easier to get a classification spectrum of, or it's fast and it's more interesting. So there's all kinds of biases that go into this in principle. But again, because we've been very careful about our systematics, because we're convinced we've found everything regardless of time scale, regardless of luminosity, all it needs to do is meet a certain magnitude threshold and meet our quality and purity cuts, which we can empirically measure the impact about what fraction of things that we lose due to those, because we know the survey footprint on the sky. It's about a third of the sky at any given time because we know the effects of extinction. We largely avoid the galactic plane. but we can correct for the limited non-extinction that's there. So we can apply these corrections and basically calculate the rate of things as a function of their absolute magnitude. Because the one thing that you can't avoid is that you always have a bias in favor of things that are more luminous because you can see them out to greater distance, but that's something that you can correct for. And
Right.
so what that allows you to do is to build up sort of a luminosity function going from the bright end to the faint end, or vice versa, if you prefer, to count the number of things that are brighter than a certain absolute magnitude within a certain detectability volume, and do that volume division and actually measure the rate over the period of the survey.
Mm-hmm.
And so again, like pretty much everything in this paper, this is really a teaser. We're going to do this in much more detail in the future. We're going to break this down by category and subcategory. We're going to compare different rates to each other and learn things about the supernova parent population, et cetera. But for the time being, we just want to show that this is something that we can do for the broad categories of objects. So we have the type 1As and we have the core collapse supernovae. And on the left, we have the cumulative rate, which is not super interesting for the plot itself. Largely, it's just interesting what it converges to. So if you build up the rate from right to left, you keep counting up the things as a function of how faint they are, how bright or faint they are. Eventually, when you get all the way through the whole population, you have some luminosity function, and eventually there's, as supernova don't go all the way down to the luminosity of a candle. There is some minimum luminosity for a supernova. Eventually you reach that point and you converge to the total rate. And so you can measure the total rate volume in the whole universe.
Yeah.
And so for the supernova rate, we come to a number that is quite consistent with previous surveys, which is good because type 1A supernovae are one of the easier things to measure. They actually have a pretty well-defined luminosity. There's not a whole lot of faint ones that are hard to find, and they're bright, they're common, et cetera. So it's good that we are able to replicate the numbers out there. And the core collapse supernova rate is harder because they do have a really broad luminosity function. There are faint ones that are not the majority of the ones in your survey, but nevertheless are the most common ones in the universe. And so your rate statistics are largely dominated by the uncertainty about the faintest things. But nevertheless, we think we have just barely managed to get enough of the faintest ones to make that measurement. Mm-hmm. And we're able to come up with an estimate of about 10 to the 5 per cubic gigaparsec per year in the low redshift universe, which is again consistent with most previous estimates, but we think we have a better handle on most of the systematics than in comparison to previous surveys. And this number is an interesting one because there's clear predictions for what this should be, because we think we know the star formation rate density of the universe. We think we know that stars above 8 solar masses should all explode, or at least collapse compact objects. And if most supernova are successful, then those two numbers should essentially agree. If like some simulations, at least in the past, would suggest, and many or most supernovae don't actually, or many or most massive stars actually don't collapse to make supernovae, they collapse directly to a black hole or something like that. If that was really, really common, we'd see a big mismatch. There were some earlier papers saying there might be a mismatch. We don't yet see that at high significance in the numbers that we have so far. So this is, again, a stay tuned thing. We're getting larger numbers. We hope to address this in more detail. We hope to look at different classes and subclasses, et cetera, to address this in more detail, but there's at least not an obvious, a big gulf between the forecast supernova rate from star formation rate density in the IMF and the observed one.
Very cool.
And then over on the right is just the luminosity function, which is the differential numbers per luminosity or per absolute magnitude. And so the type 1A is a nice well-peaked thing. There's a very characteristic absolute magnitude for type 1As around -19, with very few things that are much more luminous than that, and a slightly larger number of things that are less luminous, but nevertheless clearly less. The core collapse supernova rate, as you can clearly see, is much broader. There are really, really luminous ones. Those are the superluminous supernovae. And there are some faint ones, which we don't have great estimates on the rate of, but we're continuously improving those numbers and hope to make a better measurement of this in the near future.
Nice. All right.
Yeah, and then that brings us to the last figure and the last bit of science that we try to produce, or at least tease on, which is the host galaxy population. So because we classify everything regardless of location, if it's a very fast transient that doesn't pass the purity cut on the basis of it having a supernova-like timescale, we do require it to be in or near a galaxy, but for most supernovae, they easily pass regardless of where they're located. So we think we're pretty much unbiased in regards to whether it's in a nearby bright galaxy and to whether it's a faint dinky galaxy. whether it's a low redshift galaxy, a high redshift galaxy, or even in no galaxy at all that's discernible anywhere nearby.
Yeah.
And so we can produce what we think are pretty good constraints on the underlying galaxy population that produces different types of transients. And so ideally, what you'd like to do is you'd like to build up multi-wavelength SEDs, do SED fits, even take some spectroscopic constraints of everything, produce star formation rates and masses and stellar population ages and metallicities. And we do plan to do that in the future. That's being done right now. But for the time being, just because, again, we're just trying to use all the science that can come out of a survey like this, we've done a much more basic thing, which is a simple color magnitude diagram of host galaxies of different populations, just to see what interesting might be in there. So on the left, we have the type 1A supernovae, which are in orange, versus a effectively volume limited sample of Sloan galaxy, Sloan Digital Sky Survey galaxies that have been weighted to kind of mimic a volume limited sample.
Okay.
Because of course, supernovae explode randomly in galaxies, so they should pick out galaxies in this sort of volume limited same sense, convolved with however the supernova like to occur. Do they prefer old galaxies or young galaxies or whatever? Right. And so if you're not sure what kind of population something is coming from, and you're just doing a basic comparison, you start with a volume limited galaxy sample. Yep. So that's what we got here. And the type 1A supernovae basically trace host luminosity pretty well. So, you see the same kind of double peak pattern. There's a red sequence in the top right. There's a blue cloud in over on the left. They basically follow the host light pretty well.
Yep. All right.
These histograms here are weighted by luminosity because supernova come from stars. The larger galaxies should make more proportionally. So we've also folded that into those kernel plots on the axes there. So, we're not trying to go do any models. People do single degenerate, double degenerate delay time models. That's all sort of second order stuff. Then you really do have to do some more categorization here. Here, we're just basically showing, supernova when I follow the light to first order. Yes. So the more interesting scientifically plot is the one on the right, which shows core collapse supernovae, and we've separated them between the type 2s and the type 1 BCs by color, and also compared them to a host galaxy light in a similar way. And so there are, in some of the very simplest models for stellar evolution leading up to supernovae, you might expect that type 1 BC supernovae to be coming from higher mass stars because they have stronger winds, and also B, coming from higher metallicity stars because, again, those have more effective winds because the metals contribute to the opacity, and the opacity contributes to the line-driven winds. So there are some simple models for if the primary way that the envelope is stripped to remove the hydrogen before the star explodes and therefore produces a type 1b or 1c supernova instead of type 2b supernova, that might be more effective at high metallicity. And because there's a mass metallicity relation, high metallicity galaxies tend to be more massive galaxies. And so they'll kind of be over on the right of this plot. And so here we're looking to see, is that actually the case? Can we easily statistically discern a clear host galaxy separation between type 2 supernovae and type 1b supernovae? And while the type 1 supernovae are a little bit over to the right, if you look, that's actually not statistically significant at the sample size, which is not a small sample size. It's well over 100 supernovae here. And so if that effect is present, it's a weak effect. And similarly, in terms of color, the color is kind of reflects the star formation rate, intensity, how many young stars versus old stars. And so if you have a very, very young starbursting galaxy, it's going to have a very blue color. We don't see any obvious trends down there either. You see just as many type 2s and type 1b supernovae in these sort of ultra blue galaxies, these starbursting galaxies at the bottom, than you do in the more ordinary galaxies. So there's not any really obvious evidence in support of the idea that type 2 or type 1 BC supernovae are either younger or higher metallicity than the type 2 supernovae, which probably tells us that its binary evolution is more important than these simple single star models in separating these two classes.
Yes, indeed. Very cool.
And so we do some statistics here. For example, in table 2, you see it's broken down based on color and magnitude into red sequence, green valley, blue cloud, and other things that people like to talk about. And there's no big differences between the different core collapse subpopulations there. There are, of course, differences between the type 1As and the core collapse supernovae, which is not surprising at all. The type 1As are happening in ellipticals and dead galaxies, which core collapse supernovae do not at all. An interesting question is how many supernovae of core collapse supernovae are happening in sort of red and dead galaxies that you might call an elliptical and don't have any obvious star formation. That again is a subject of a different paper that's out by either Arani and other people in the collaboration, but we can touch on it here as well, since again, with a big survey like this, you can at least touch on everything pretty quickly and easily. It's not many, but it's not zero. So there's a little bit of residual star formation, or perhaps other channels of producing things that look like core collapse supernova that are actually something quite different in these galaxies.
Cool. All right.
So yeah, that's basically the paper. It's again, it's largely a teaser. We show what we're doing. We try to convince you that we really are complete to the extent that we say we are, down to the magnitudes, and after applying the cuts that we need to apply to reach that high completeness, we show some results on rates, luminosity functions, host galaxy properties, and then this general wonderful parameter space that we're starting to explore, which is only one of many potential parameter spaces that one could explore. For example, color, rise time separately from fade time, et cetera, are all different parameter space plots that could be made, that will be made in future papers. And so you can look forward to that. So the last thing I'm just going to say here is I want to emphasize that this is actually really meant to be a public project. So this was a summary of the first 2 years of what we did, but the survey is continuing now, and will continue for another several years. And as it goes, and as we classify things, as we discover things, we are making basically everything public. So we make the light curves are public automatically through the alerts. The classifications are being made public through the transient name server, TNS service. And then finally, if you scroll to the very end in the appendix, we're also making our catalogs public on a web page.
Yes.
And so I think that the URL is right there. You scroll past it, but it also appears later. And so here's a web page. The web page has changed a little bit, but largely it's it looks the same way as it does below. It allows you to either just simply produce a catalog of everything if you set the most general options, or if you don't want to be thrown up with thousands of candidates all in your browser all at once, you can subset that to something interesting. So here, for example, it's only showing core collapse supernovae. It's only showing things that pass the quality cut and the purity cut. So they're going to have good light curves. Their measurements are actually going to be believable for the rise time and the fade time and the total time and the luminosity at peak and so on. It has the option to display a host galaxy thumbnail, so you can quickly by eye see what kind of galaxy it's coming in and where in the galaxy it's happening from those little crosshairs that you can see. One of them is the P48 image at the scale of the telescope. The other is a host galaxy image that is at the constant scale of pixels per kiloparsec. It shows a light curve plot, and it shows coordinates and peak magnitude, peak absolute magnitude, and those timescale properties, and of course the redshift and classification. And other things can be displayed as well, depending on what is of interest to the user. And so it's a very fast web page. We really encourage people to go there, make use of it, select subsamples of interest to you, write your own papers if you want. This really, this project was in a large part publicly funded, and the community should be able to use everything that comes out of it as much as possible. And so this is one of the ways we're trying to help people do that.
Very cool. Very cool. Dan, I want to thank you so much for walking us through this really lovely paper. And you touched on it a couple of times. So this was 2, and this was a little less than a year ago. So I imagine that there'll be numbers 2 and 3 on these bright surveys. So sort of, you don't have to spill your next research projects or something like that, unless you want to get a little free advertising. But where do we go, let's say, over the next couple of years on these surveys?
Yeah, so paper 1 was largely just the project itself. Here's the telescope, here's the survey, here's what we're doing. Here's the very first few months of the project. And then for some science, we also said some things about the fraction of galaxies in which we find supernovae that have catalog redshifts versus uncatalogued redshift, as a way to probe how well we have actually mapped out galaxies in the nearby universe. But of course, as I mentioned many times, we have more papers planned in the works, or which have already come out since this paper did.
Yes.
Some of them will be in the numbered sequence. Most of them won't be, because this really touches on everything that the Zwicky Transient facility is doing. Not all of it is based entirely on the Bright Transient survey, this magnitude complete effort, although almost every project is making use of what we're doing in terms of acquiring so many classifications in some way.
Yeah.
But so, for example, there will be a paper that is specifically about detailed light curves that should hopefully be coming pretty soon, which is going to take the photometry that's coming off the telescope, and not just the alert photometry, but actually doing force photometry, since we actually know the specific position of each supernova. You can recover things below the nominal 5 signal detection limit of the difference imaging. And you can also do slightly better photometry in general with this approach. And really just characterizing the detailed light curve shapes of all sorts of different objects, and producing a gigantic sort of final catalog of, here is all the photometry that ZTF has gathered on all the bright supernovae that have happened since 2018 in the Northern Hemisphere. So that'll be a big data paper as well that we hope to put out in the relatively near future. There will be also accompanying paper on sort of final classifications. So these are classifications that we put out to TNS. They're pretty reliable, but there are obscure types, and there are subtypes of supernovae that are very hard to approach without a much more detailed investigation of distinguishing the various 1A subtypes in particular. It really takes expert attention to do that well. Yeah. And so we're also working on that, and we're going to put out a paper that tells the final classifications of everything to more be able to get at questions of rates of subtypes and not just the basic types. We're also going to be having a paper on the host galaxies in more detail. So again, this was just a color magnitude diagram to say some basic things about type 1A versus type 2 versus type 1BC. But we also want to say things about, say, type 1C broadline versus type 1C. And we want to also look at real physical properties, not just color and luminosity, that are more insightful. And so that is in the works as well.
Very nice.
And probably many papers beyond that we haven't yet mapped out, but those are a few that we are currently writing.
Very cool. Very cool. Dan, I want to thank you so much again for walking us through this ZTF survey. It's very awesome. And everyone, that will do. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.